embedded stochastic processes is about concealing one process within the other. So let's say you have a process y of t. Let's say it is Whiteson stationary. That means so it's a well-behaved RYY tau is expected value y of t, and y star of, let's say, t plus tau. So t2 minus t1, right, is ry by tau. Then we have another process. Let's say this is not stationary. And I'm going to conceal x within y in this manner and create a new process z of t. So this has interesting radar applications, but in any case today we just want to look at its match filter and autocorrelation properties. So in general, if you look at RZZ T1, T2, that's expected value of ZT1, ZT2 star, but Z is so Z is expected value of Y of XT1, Y star of XT2. So we have too many random stuff going on, x of t and y of t, etc. So I'm going to do this condition. So this is expected value, the conditioned expectation, y of x of t1 multiplied by y of x of t2 conditioned on xt1, xt2. And then get rid of the condition. So let's look at the inner. So if the xt1 and for a given xt1 and xt2, this we can write it as ryy from here. This is, if this is t1 and this is t2, then this is t2 minus t1. That's the white stationary. So this would be expected value of RYY. This will be x of t2 minus x of t1. So RYY x2 minus x1 given x2, which is x of t2, and x1, which is x of t1. So this is what we need to complete. But if you come here, so going back to tau here, so if this is Whiteson stationary t2 minus t1, I'm going to call that tau. So this is t2 minus t1. So if it is Whiteson stationary, it also has a power spectrum. So the power spectrum RYY is the Fourier transform of this gives you SYY omega, or RYY omega. You can get it from SYY omega by this expression, inverse Fourier transform. I mean RYY tau. So this expression, I can use that integral to rewrite this expression as 1 over 2 pi integral SYY omega e to the power j omega x2 minus x1 given d omega x2 x1. We need to compute this. So the expectation is clearly because of these random variables. So this I can rewrite this as 1 over 2 pi integral SYY omega expected value of e raised to j omega x d omega, where x is x of t2 minus x of t1. And t2 minus t1 is tau. So now everything depends on the properties of how to compute this. So at this point, let me assume x of t to be a Gaussian process. Let's say non-stationary Gaussian, like Brownian noise or something. So it's Gaussian with some autocorrelation function. I'm going to try this function first. So it's non-stationary because the autocorrelation function is, this is Rxx t1 comma t2. So that's a non-negative definite function, so that's certainly an autocorrelation function. So let's, so if x2 is Gaussian, then this is a Gaussian random variable. So the question is, let's say it is zero mean. So this is certainly zero mean. And the only thing we need to figure out is what's the variance of this random variable. Because this expression now would become 1 over 2 pi integral sxx omega, the characteristic function of a Gaussian random variable. So that's e raised to minus omega squared sigma x squared by 2 d omega. Sigma x squared will be a function of t2 and t1, t2 here. So expected value of x is 0. So variance is expected value of x squared. But that's expected value of x of t2 minus x of t1 the whole squared. So if you expand, that's expected value of x squared t2 plus expected value of x squared t1 minus 2 expected value of xt1, xt2. There is no need for star because this is a real process. But the autocorrelation of Rxx t1 comma t2 is alpha t1 t2. So this will be alpha t2 squared plus alpha t1 squared because t1 t1 minus 2, this is Rxx t1 t2. That is t1 t2. So that's alpha multiplied by t2 minus t1 the whole squared. So if you call this to be tau, this is alpha tau squared. And for a Gaussian function, we can replace it here by so sigma x squared is alpha, so this becomes minus alpha omega squared tau squared by 2 d omega. So this expression needs to be computed. But this is, so this first of all shows that RCC is also Whiteson stationary. I mean, Z of t is a Whiteson stationary process, and its autocorrelation function, which will tell you how good the match filter output is in terms of compressing the pulse, turns out to be. So you can do a lot of shaping this by selecting SY by omega and making sure that the concealed function is a Gaussian non-stationary function. So this is alpha omega squared tau squared by 2. So notice that when tau is 0, this is 1. So essentially that information is squeezed through and it's shaped by the SYYs around the peak behavior. And for large values of tau, this kills off everything else. So the R tau, irrespective of this RCC tau roughly has this shape. And its compression properties can be modified by fixing the value of alpha, and also to an extent by the outside stochastic process y of t. So compression properties can be modified by adjusted using this modulating function inside x of t. So for example, if you take this to be Gaussian, but let's say Brownian noise, then this will be the autocorrelation function will be alpha min of let's say t1 comma t2 minimum. And that if you take here, so if t2 is greater than t1, then you only have to redo this. T2, minimum of T2 is just alpha T2. Minimum of T1 is alpha T1. Here you have two situations. T1 greater than T2. So this will be 2T1. And T2 greater than T1. So that will be T2 will be minimum. So this case will be sort of alpha. Alpha goes away. So T1 is greater than T2. So the minimum is minus alpha minus 2 alpha T2. So this will become alpha times T1 minus T2. But T1 is larger, so this is positive. Here T1 is smaller, so this will be minus 2 alpha T1, and basically this will come T2 minus T1 multiplied by alpha, because the T2 minus T1, so that's also alpha tau. So essentially the variance will turn out to be alpha absolute value of tau, and this expression comes out to be like this. So this is the Brownian motion is in terms of the match filter compression. This is weaker compared to the previous illustration with alpha T1 comma T2. So if you can manage to generate once you manage to generate a Gaussian process, then that can be used on the transmit waveforms, and it has got some interesting compression properties and also other useful behavior.